Thank you very much. Hey everyone, great to see you all out here. Thanks for the nice introduction. My name's Michael. I'm one of the original engineers on the team that built the Avalanche Bridge. Going after Stephen, I did not put an introduction slide in, but if you'd like to know anything more about me, please feel free to come up and ask after the fact. So today we'll be talking about the Avalanche Bridge design, a little bit more about bridges in general, and also how we adapted it to support Bitcoin as of last month. So to start off, at the beginning, what are bridges? In case anyone is not familiar, bridges are a way of moving your tokens from one blockchain network over to a different one. And while that might seem super simple, it's actually a very interesting problem because two independent blockchains have no way of knowing transactions that are occurring on the other one. So if you are running an Avalanche Go node, like I hope many of you out here are, that node has no idea about transactions that are happening on Ethereum. And if you're running Geth or whatever Ethereum client you'd like, similarly, it has no idea of what's happening on Avalanche. So if you want to move some of your tokens that you're holding on Ethereum over to Avalanche to take advantage of any of the number of the great benefits that Avalanche gives you, you need to bridge it. So there's a couple different models that are common in bridges, the most common being the lock and mint model. And the way that this one works is you lock up your tokens on the native chain, in this case Ethereum in this example. And on Avalanche then you receive basically what's called a wrapped token. It's a representation that you can redeem one for one exactly for the original token on Ethereum should you want to go back. So the very important thing in this model, really in both models, is who is holding the lock. If only a single person is actually able to access all of the collateral that's supposed to be backing all of the wrapped tokens one-to-one, you could end up with a very dangerous situation where they might suddenly have an island named after them, then they're never seen again. The second common model is a pooling model. Instead of minting a wrapped token, which is a new representative asset, you have two assets that you assume have the same price on two different chains, and you can actually create what are called pools on one chain or the other, such that when you deposit into the pool on Ethereum, say you deposit your USDT, you're able to redeem the same amount of the like token on the other chain. The key difference here is that the tokens already exist on both chains. And this one is actually more difficult to maintain because someone needs to make sure that the pools are never run out. If you have any sort of directional flow from one network to the other, one pool would fill up and the other one would empty out, and the bridge wouldn't be functional at that point. And for that reason, the lock and mint model is far more common. Really, in both models, though, the key component is what is sitting in between the two blockchains. Like I said before, the one blockchain has no idea what's happening on a different blockchain. So you need to have some sort of bridge node, validator, relayer, warden, whatever you'd like to call it, some sort of bridge validator that is monitoring both networks and is able to react to what happens on one network on the other one. So you might be asking why you want to bridge your funds. There are any number of different reasons, but the most common ones are to use applications that are only available on a specific chain. If you have BTC and you're holding it on Bitcoin, you likely can't take advantage of really anything because there aren't DeFi apps available on the Bitcoin blockchain, and that's really great incentive to move it over to a chain like Avalanche, where you could earn yield on it. You also might want to bridge to avoid paying high fees, or, like I said, take advantage of yield opportunities that might exist. This picture was credit to the Avalanche intern. I'm actually not sure who runs that Twitter account, but it has some great memes, so I thought I'd take one. Are bridges secure? This is a very hotly contested question, I think, and I think it kind of speaks for itself given all of these recent headlines that I'm sure you've seen. If you sum up the three of them, over $1 billion has been stolen from bridge as a result of bridge exploits in just 1 year, just this year, the first half of this year for that matter. And if you're bridging your tokens over to a different network, in order to get 5% more yield, that's great. But if you're taking on the risk of bridging it and potentially losing all of your tokens on the native network, it might not be worth the extra yield that you're getting. So there's a lot that goes into bridge security that I'd like to get into a little bit. The first part of it is really that a bridge is only as secure as the teams that are behind it. Bridges really started maybe 2 or 3 years ago. Very new technology, very, it hasn't been fully developed yet, and it's not fully matured to the point, or some of them haven't necessarily matured to the point where they are safe holding billions of dollars of value. So you really, I think, more so than any of the specific exploits that might exist in any specific bridge, it's just about the space maturing, being properly audited, having the proper test coverage. All of the really boring things that developers like to skip over in order to deliver a product are really the most important part of making a bridge secure. So generally speaking, I mentioned how every bridge needs to have some set of validators that is monitoring both blockchains. The more bridge validators that you have generally means the better security that the bridge should have. And the reason being that if you have only a single validator, that's a single point of failure. If someone's able to compromise that one entity, they could take control of the whole bridge. If instead you have 1,000 validators and you need a certain threshold of them, say 750 of them to agree, then you need to compromise that many more parties in order to actually execute an attack on the bridge. The exception there being that there are hacks that could work for not needing to take control of all of the validators. So if you could easily impersonate a validator, or if you could somehow bypass a check of the number of validators that actually confirmed a transaction, then you could get around executing an attack on a bridge without actually taking control of the full validator set. So that's another very important property to consider. Yeah, and there's really a lot of different levels of bridge security, as I said. Starting at the blockchain level, I think Vitalik had a great post about this a few months back. No matter how secure your bridge is, if the blockchain network that you're connecting is susceptible to 51% attacks for a relatively cheap cost, then your bridge will be no more secure than the networks that it's connecting. If someone could perform a 40-50 block reorg on Ethereum, there are a lot of bridges that would be susceptible to this type of attack because the validators would think that a transaction had occurred on Ethereum, and then if it gets reorged out and didn't happen, that could potentially put the bridge in a bad state. Yeah, so that's the very base level of the security of a bridge, but it's actually not where any of the attacks or hacks on the previous slide were executed. Those happened at the smart contract and infrastructure level. So many bridges take advantage of smart contracts on various chains in order to aggregate approvals of the validators. If there's some type of voting mechanism that goes on, a lot of times that is put on chain in the form of a smart contract. And obviously, if that smart contract has some sort of bug in it, if it has complex logic that might not have gone through formal verification, then that could put the bridge at risk. And then finally, kind of the most boring part of a bridge security is the infrastructure level. Who has access to the machines that the bridge is running on? How easy is it to phish them and take control of those machines? It's not necessarily the exciting security aspects of Web3, but in many cases, it can really result in devastating consequences if you don't have secure infrastructure. So in order to build a secure bridge, you really need to focus not just at any one point, but at the full stack of the bridge and make sure that you're constantly improving and making all of your processes more secure. Yeah, so getting onto the Avalanche Bridge, which is what we built, what sets that apart? The key innovation here was our use of secure hardware. In our case, we use Intel SGX, that's software guard extensions. You might also hear it referred to as enclaves or trusted execution environments. But the key idea is that we have this secure hardware that provides us with execution integrity, data confidentiality, and code attestation. So what does that all mean? Typically, when you are running a program on your computer or on a server that you control, you are able to do whatever you want to that program. You can read its current values, you can alter its execution, and really you can take arbitrary control over what's happening on your own computer. With secure hardware, your application is actually run on an isolated part of the chip that is not able to be tampered with, and it's isolated from even administrator level access. So the underlying operating system or an administrator on the machine that it's running isn't able to see the values of the program as it's currently executing. They're not able to alter or tamper with the execution of that program. And so this is an extremely powerful property when you pair it with code attestation or remote attestation, because a third party is actually able to then perform attestation that you are running a specific version of the program on a valid, secure hardware instance. And that just really turns the trust model of our bridge on its head. So when you think about distributed systems and Byzantine fault tolerance, typically you're not able to know if a remote party that you don't control is behaving honestly or not. But when you take remote attestation and secure hardware environments into account, you can actually get proof that they are running the code that you expect them to be running within a valid trusted execution environment or hardware environment. And that really just does wonders for the trust model. Yeah, and so in addition to Intel SGX, we also have a great set of third-party chain oracles. We call them wardens. I mentioned them before about monitoring one blockchain to relay what happens on Ethereum over to Avalanche and Avalanche back to Ethereum. So the wardens monitor the supported blockchains. They report transfers to be processed by the bridge to the enclave, for the enclave actually to process them by generating the transaction to be sent on the opposite network. They perform attestation of the enclave, so they make sure that the enclave is running the expected code that will carry out the bridge function honestly and not steal the money. And they also store a piece of the enclave key information. So when it comes to secure hardware, obviously we would never expect there to be some type of hardware failure where we lose, or where the hardware becomes corrupted somehow and loses its state. But you do have to plan for that scenario. And so in our case, each of the wardens stores 1/8 of the enclave's secret, and it's split up in such a way that you can recompute the secret if you have 6 out of the 8 wardens actually agree to provide the enclave its secret share. And so that way we have decent fault tolerance. Another key differentiator is who the wardens actually are. So we have 8 partners, really 7 partners plus Alpha Labs, to run wardens. I think it's a really impressive set of people of companies that have signed up to be our partners and run wardens, not only because they're all blockchain native, but they have a great experience with security in terms of obviously Halborn's the auditing firm. Avscan is very familiar with the Avalanche ecosystem from day zero, and just a great breadth of different companies within the blockchain infrastructure space. It's really was exciting to see how many were willing to sign up to work with us. Yeah, another great differentiator now as of last month of the Avalanche Bridge that we support Bitcoin. So we announced it back in Barcelona that we were going to be adding Bitcoin support, and we shipped it last month. So we were able to deliver on that promise, which is very exciting. You might be wondering why there aren't many other big Bitcoin bridges out there. So Bitcoin obviously is the highest market cap of any crypto asset, but it also has really the fewest applications available for it to be used in, which really just makes it the most obvious candidate for wanting to bridge it over to a network like Avalanche, where you can take advantage of, one, the fast finality. You don't have to wait for 10 minutes for your transaction to go through. It's just a second. You can take advantage of all the applications available on the C chain, earn money on your Bitcoin that you're holding. So why aren't there other Bitcoin bridges? Why do we see a bunch of bridges between different EVM networks and different networks that support smart contracts, but not Bitcoin? And I think the reason is mostly for a number of technical challenges that I'll get into now. So one, the biggest one is the lack of smart contract support on Bitcoin. So I mentioned earlier how many bridges take advantage of smart contracts in order to aggregate approvals from the bridge validators or have other sort of validation logic that the bridge is functioning, or that implements the bridge functionality. On Bitcoin, there is no smart contract support. In order to use a multi-sig, you have to come up with a special Bitcoin script. You can't do approvals on chain. It really limits your ability of what you can actually do just by the fact that Bitcoin doesn't support these types of operations. The second is the handling of UTXOs. So I'm not sure how familiar you are with all the different virtual machines in the blockchain space, but in the EVM on Ethereum or on the C chain, you have an account-based structure where you have a single address and you send transactions from that address. So if you're holding, if you have 5 USDC on Ethereum and then someone sends you 5 more USDC, you can send a generic transaction spending 10 USDC from that address without specifying the specific inputs. All of the Ethereum nodes know that a specific account has a certain balance. On Bitcoin, it's entirely different. You don't just have a balance, you actually have discrete UTXOs, unspent transaction outputs, that you have to specify you are spending when you send a transaction. So if Patrick sends me 5 Bitcoin and Steven sends me 5 Bitcoin, feel free to do that after this. Then to spend the 10 Bitcoin, you have to actually specify the exact transactions inputs that you are spending, and then specify the outputs as well. So it's not just balance-based per address. Each transaction specifies its discrete inputs and outputs, which is an entirely different transaction model. It has its own benefits and its own drawbacks, but in terms of building a bridge, it makes it significantly more difficult when all of the other major smart contract platforms out there use the account-based model. And then finally, the other main technical difference is that you have different address types. So on any EVM-based chain, you can use the same address on multiple different networks. But for Bitcoin, they have their own address types, actually a number of different address types. So it makes it difficult for bridges to know where to actually mint the wrapped funds on the opposite network, because the address that sent the funds does not line up with the address that's receiving the funds. So taking all that into account, there are a number of projects that have attempted to build some sort of L2 or bridge for Bitcoin. I list a few of them here. I think the most interesting part about all of the ones that I list is that by far, by an order of magnitude, the most popular one by market cap is WBTC. Which is a fully centralized KYC'd custody solution. So you have a single company holding a bunch of Bitcoin and minting the WBTC on Ethereum. They know who is receiving, in terms of KYCing everybody who is receiving the new WBTC that is minted. That's a perfectly fine solution, but it really goes against the ethos of the crypto space in terms of anyone being able to transact easily and without these walled gardens. But despite that, it's by far, I think by almost 10x, the most popular of all these ones listed. And so it really stood out to us that this was a huge opportunity to create a product that made it easy to take advantage of your BTC on a different network. We wanted to make it just as intuitive as bridging any of your other tokens. We wanted to make it distributed and secure, and we really wanted to enable people to use their Bitcoin on Avalanche. So how do we do that? In terms of the challenges on the previous slide, one, the Avalanche Bridge has no need for smart contracts on the native chain. And the reason for that is because all of that logic is moved into this secure enclave environment. So when funds are locked in the Avalanche Bridge on Ethereum or on Bitcoin, they're actually not locked in a smart contract, as the case with most other bridges. They are locked in a wallet that is controlled by this enclave and nobody has access to. The 6 of 8 wardens have to approve any changes to the enclave. So instead of being locked on chain, they're being locked off chain, which really enabled us to have a lot of flexibility in how to design this bridge. In terms of managing UTXOs, we pushed that problem out to the wardens. So the wardens automatically manage the UTXO set controlled by the enclave. They optimize which UTXOs they want to spend and when they're receiving them in order to reduce dust and the transaction fees crossing the bridge. So we also wanted to make sure that we keep it relatively inexpensive. And then finally, in terms of the different wallet addresses on both chains, this is a technical detail that many of you might not be interested in or even realize, but we actually use the same user wallet in terms of the private key on both networks. And the way that we determine the C-chain address to mint funds when a Bitcoin address provides the funds is that we recover the public key from the signed transaction on the Bitcoin network, and then we convert that public key into an EVM address. So you can imagine, really I think of a wallet as a single public-private key pair, but the address is neither the public or private key, it's a hash of the public key. And from a signed transaction, you can recover the public key of a wallet, not the address, and then from that public key, you can derive what any of the various address types would be. So it was a cool technical detail that we worked into the bridge to help smooth out the user experience. In order to actually implement this on the front end, we needed to build our own wallet, but fortunately we knew some guys who were doing that. Knew some great people who were building the core wallet extension, and I think Nick is going to talk about that after this, so I won't step on his toes at all. But we were super excited to see the Bitcoin bridge go live within the core extension last month. And then lastly, I think I have just a few seconds left here, but you might be wondering, we built this bridge we think is a key innovation for enabling cross-chain transfers using this secure hardware. Can't we apply this secure hardware solution more broadly within the blockchain space? And if you ask me, the answer is absolutely yes. There's no limitation to the number of use cases of this trusted execution environment technology. It doesn't just need to be bridging. You could use it to build any number of cool applications and really work it into your security model as a piece of the solution to make your project more secure as a whole. So whether it's more trustworthy trading applications, whether you want some random number generation, Oracle networks. I don't want to drop too much alpha about what we might be working on in the future, but there's really a lot of more possibilities that we could do here, and that's what makes us excited to keep building. Yeah, so that's all I had. Happy to answer a couple questions if we have time, though. Don't all jump at once.
Could you tell us a little bit about the periodic key rollover that was announced a couple of weeks ago?
Yeah, absolutely. So you might have seen that the periodic key rollover announcement a couple of weeks back with the bridge address change. What we were doing there, the main security upgrade was that when we originally launched the bridge, we had 4 wardens, where 3 of 4 wardens needed to approve transfers across the bridge, and we wanted to move to a model where we had 6 of 8 wardens. But in order to do that, we needed to invalidate all of the old secrets. So we didn't want to just generate new secrets and keep the same address, because no matter what, the 3 of 4 old secrets mathematically could be used to recompute the secret that's being used. So we moved, we had the enclave generate new secret shares and migrated the bridge to those new addresses in order to improve the security of the bridge as a whole. That's something that could happen again in the future. I think we'd be looking to expand the warden set as much as possible. So, yep. Yeah, in the back. Sorry, what was the first part? Yeah, so the question was, are the wardens using threshold encryption for their key shares? And then I guess the second part was, what if 3 of 8 of them go offline? Yeah. Great question. So the wardens do encrypt all of the secrets that they have with various other keys that we have them generate, where we get the public key and they have the private key, but they don't use any sort of threshold encryption or threshold signature scheme. Threshold signatures could be used to design a bridge with similar functionality, but that's just not the design that we took. It's certainly something that we have explored and I think can continue to look into in terms of working it into various different components of the solution, but it's not currently threshold signatures are not currently used in the bridge. And then if 3 wardens go offline, it was the second part of the question, which is definitely a case that we considered. If 3 wardens go offline at the same time, yeah, you won't be able to perform new transfers across the bridge, but we have a number of backup mechanisms in place such that they would be able to come back online. Each warden has their own backup mechanisms, but the bridge also has other mechanisms built in that I'd be happy to talk about later. It gets into the technical details of it pretty quickly of how you can securely store secrets of an enclave without exposing it outside the enclave at all and persist it across multiple hardware instances is an interesting challenge that we have thought through of solutions for. Awesome. Well, I think that's at time. So thank you very much for the questions. Great audience. See you all outside.